Hello everyone, this is Infinity Vision and my name is Rehan Nawaz. Today in this lecture, we are going to discuss ratio in a very comprehensive manner. This lecture is meant for the students of class 10th who are planning to begin their IIT JEE preparation this year. When you begin your IIT JEE preparation, you should always start by looking at the syllabus of IIT JEE. And when you look at the syllabus of IIT JEE, especially the mathematics syllabus, you would see that there are chapters from algebra, there are chapters from trigonometry, there are chapters from analytical geometry, and there are chapters from calculus. For mastering and understanding these chapters, you are expected to have a mastery over some of the fundamental ideas. These fundamental ideas act as a bridge of what you already know to what you are going to study during your IIT JEE preparation. These fundamental ideas also act as tools for solving many of the problems of these chapters. Keeping that in light, we are bringing you a series of lectures which will help you develop a mastery over these fundamental ideas. So when you are going to begin your IIT JEE preparation, which is a long journey, you should always begin in a very confident manner. And these tools are going to give you a lot of confidence. So we welcome you to this course so that you start your IIT JEE preparation in a very confident manner. What is ratio? Ratio is generally defined as a relation between two physical quantities of same kind. Let's say you have two quantities A and B and they are of the same kind. And let's say you are going to define a ratio between A and B. So you are going to represent it as A colon B. Now these two terms are the first two terms of the ratio. This is called antecedent, the first term. And the second term is called consequent, in this case, which is B. So ratio can be defined as a relation between two physical quantities of same kind, which is represented as A colon B, where A is antecedent and B is consequent, and it means that what multiple A is of B or what part A is of B. Let's say you have to find the ratio of two lengths, first length being 4 feet and the second length being, let's say, 3 yards. And now you are expected to find the ratio between these two lengths because they are of the same quantity. What you need to understand that the first length is given in the unit of feet and the second length is given in the unit of yards. To find the ratio, you always bring both the quantities with a common unit. So definitely you need to either convert feet into yard or yards into feet. And I'm sure many of you know that 1 yard equals 3 feet. So what we can do, we can convert 3 yards into 9 feet. So this ratio will be actually 4 feet is to 9 feet. Now it is more sensible to now tell that what part of length A is of part B, and you can simply find it by dividing it, which you can say 4 is to 9, or you can say the first length is 4/9 of the second length. What are equivalent ratios? You must be remembering your rational number class and you must be knowing what are rational numbers and also what are equivalent rational numbers. Let's say you have a rational number 2/7 and let's say you want to multiply the numerator and denominator both by 6. So you got something like 2 into 6 and 7 into 6, which is 12/42. So you can say 2 by 7 and 12 by 42 are equivalent rational numbers. Same way, when you have a ratio A is to B, let's say, you have antecedent as A and consequent as B. And let's say I am going to multiply the antecedent by a quantity M. And let's say I am going to multiply consequent B with M. So antecedent and consequent both are multiplied by the same number. So I can say A is to B is equal to AM is to BM. So when you multiply antecedent and consequent with the same number, you get the ratio which is equivalent to the original ratio. How do you compare two ratios? In the same way we compare two fractions. Let's say you have fraction 2 by 7 and let's say you have another fraction 3 by 8. How do you compare that which of the two fraction is bigger or smaller? What you do, you try to bring them to a common denominator. So you take the LCM of 7 and 8, that is 56. So you're going to multiply your first fraction with 8 by 8 and the second fraction with 7 by 7. You get an equivalent version as 16 by 56 and you get the equivalent version as 21 by 56. And now you see that the denominators are 56. By looking at the numerator, you can say that the second fraction is bigger than the smaller fraction, the first fraction. Same way, when you have two ratios, A is to B and X is to Y, which of the two ratio is bigger? So what you need to do, you have to bring your ratio to its equivalent version so that their consequent are same. So when I see A is to B and I see X is to Y, I am going to convert A is to B in its equivalent form by multiplying the antecedent by Y and consequent by Y. Why did I multiply with Y? Because the consequent of the second ratio is Y. In the same way, I am going to create an equivalent version of X is to Y by multiplying with B, that is the consequent of first ratio. I'll get Bx is to By. Now you know both the ratios have same consequent. So what you need to do, you just need to compare Ay and Bx. If Ay is bigger than Bx, then A is to B would be bigger than X is to Y. If Ay is smaller than Bx, then A is to B would be smaller than X is to Y. And if Ay is equivalent to Bx, then A is to B would be equivalent to X is to Y. This is how you compare two ratios. Let's say you have a ratio whose antecedent is a fraction and consequent is a fraction or rather rational number. Let's say your antecedent is A by B and your consequent is P by Q, where A and B are integers and P and Q are also integers. You would be able to convert this ratio into the ratio of two integers simply, as you know that ratio can be seen as nothing but the division of antecedent and consequent. So I'll just replace colon with division and I'll write P by Q. And then I'll convert it into A by B into Q by P, and then you can say AQ by BP, which is equivalent to AQ is to BP. So successfully I have been able to represent my two fraction A by B is to P by Q into the ratio of two integers AQ is to BP. You have been seeing that we are taking the ratios as a ratio of two integers or ratio of two fractions. What about when antecedent or consequent, one of them becomes an irrational number or both of them becomes irrational number? We'll take some example to understand what exactly the idea is. Let's say I take the first ratio as root 3 is to 7. You can see your antecedent is an irrational number, but consequent is a rational number. And let's say second example as root 3 is to root 7. Your antecedent and your consequent both are irrational numbers. And then third example is root 3 is to 7 by 5 root 3. You have two irrational numbers, but the second irrational number is a rational multiple of first irrational number. When you will see this type of story, you know that this is basically the ratio of two integers only, because the first irrational number would be able to cut the other irrational number by a rational number. So you would be able to represent them as a ratio of two integers. So you can cancel out this case that, okay, when antecedent and consequent are irrational numbers, but one irrational number is a rational multiple of other irrational number, then they can be reduced into the ratio of two integers. But this case, when exactly one of the antecedent and consequent is irrational number, then you won't be able to convert them into the ratio of two integers. In the same way, when the antecedent and consequent both are irrational numbers and none of them are rational multiple of each other, then also you won't be able to represent them as a ratio of two integers. So far we have sought two ratios. The first being the ratios which can be represented as a ratio of two integers, and then other kind, that the ratios which cannot be represented as a ratio of two integers when one of them is irrational or both of them are irrational and none of the irrational is rational multiple of the other. Now, when you have ratios which can be represented as a ratio of two integers, you call them commensurable quantities. And when you have ratios which cannot be represented as a ratio of two integers, you call them incommensurable quantities. What are compounded ratios? Let's say I give you three ratios. The first being A is to B, second being P is to Q, and third being X is to Y. Now, if you are going to multiply the antecedents of all the ratios, and then you are going to multiply the consequents of all the ratios, you would be defining a new ratio, that is APX is to BQY, and this ratio can be called as compounded ratios of A is to B, P is to Q, and X is to Y. What are duplicate ratios? Let's say you have a ratio A is to B, and you are going to compound this ratio to itself, which means you are going to multiply with A is to B. So you are going to get a ratio called A square is to B square. You can call that A square is to B square is a duplicate ratio of A is to B. In the same way, let's say you have ratio A is to B, and you are going to multiply with A is to B, and then again A is to B. So you are going to multiply A is to B to itself 3 times. You are going to get a new compounded ratio, that is A cube is to B cube. This is nothing but the triplicate ratio of A is to B. In the same way, let's say you have a ratio A is to B, and you are going to find the square root of antecedent and consequent, root A and root B. So you can say that root A is to root B is a sub-duplicate ratio of A is to B. So this is how you are going to interpret these terms like duplicate, triplicate, sub-duplicate, sub-triplicate, and so on. Ratio of greater equality or ratio of lesser equality or equal ratio. What exactly we mean by that? Let's say you have a ratio A is to B. There is a scenario when antecedent is bigger than consequent. There is another scenario when antecedent is smaller than consequent. And there is third scenario when antecedent and consequent are equal. When antecedent is greater than consequent, you call it ratio of greater equality. When antecedent is smaller than consequent, that is A is less than B, you call it ratio of lesser equality. And when antecedent and consequent are equal, you call it ratio of equality. Let's say you have a ratio A is to B, and you are going to add some quantity X to antecedent as well as consequent of the ratio. So you will get a new ratio A plus X is to B plus X. Now the question arises that whether the new ratio is bigger than the previous ratio or smaller than the previous ratio. Let's see how we are going to analyze it. Let's say you have the ratio as A is to B, and you have the other ratio A plus X is to B plus X, since we have added same quantity to the antecedent as well as consequent. Now to compare which of the ratio is bigger, we'll start with simply finding a by b minus a plus x upon b plus x. Now, if this is positive, then definitely the new ratio is smaller than the old ratio. And if this is negative, then definitely the new ratio is bigger than the old ratio. And if the difference is equal to 0, then it means the ratio didn't change the value. Now let's say I'll try to simplify this expression. I'll take the LCM b into b plus x. I'll cross multiply a into b plus x minus b into a plus x. As you can see, a into b and b into a will cancel out each other, and you will be left with ax minus bx upon b into b plus x. Now you can see x is common, a minus b upon b into b plus x. Now when you see that the whole thing depends on a minus b now. If a minus b is positive, then it would be positive. If a minus b is negative, then it would be negative. So what did we learn? When your antecedent is bigger than consequent, when your antecedent is bigger than consequent, or the ratio is of greater equality, then you add same quantities to antecedent and consequent, the new ratio reduces its value. And when your antecedent is smaller than consequent, which means that you have a ratio of lesser equality, and you add both the quantities, same quantities to antecedent and consequent, the new ratio becomes greater than your previous ratio. And if a equals b, which means you have a ratio of equality, that is antecedent and consequent are equal, then same quantity being added to antecedent and consequent doesn't change the value of the ratio. Now let's look at the first theorem of this ratio. But before we go into this theorem, I should tell you some general point related to any theorem you encounter. Whenever you encounter any theorem, you should be able to capture what exactly that theorem is trying to say, what are the preconditions and what it implies. Because if you are able to capture the knowledge of the theorem, all the conditions of the theorem, then you would be able to apply them in the problems comfortably, and that will help you solve the problem in a very fast way. The second thing, that you cannot use these theorem as your tools until and unless you have proved it. And the moment you have proved it, that theorem becomes your own tool and you can use it as your own thing. Now coming to this theorem, let's see what exactly this theorem is trying to say. If A is to B equals C is to D equals E is to F, you have a continued ratios and all the ratios are equal, and then each of the ratio is equal to P A to the power n plus Q C to the power n plus R E to the power n and so on upon P B to the power n plus Q D to the power n plus R F to the power n plus and so on to the power 1 by n, where P, Q, R, N are quantities, whatever. Now, if you see, the first term of the numerator has been inspired from the antecedent of first ratio, and first term of the denominator has been inspired by the consequent of the first ratio. So if you notice that, okay, A has been raised to the power n and B also has been raised to the power n, and A has been multiplied with P and B is also multiplied with the same quantity. Same for C, you see, C has been raised to the power n and D has to raise to the power n, but it has been multiplied by some other quantity Q, and same with E and F. And we have to prove that this complex looking thing is also equivalent to these simple ratios. So whenever you encounter these type of problem in ratio chapter, you should always begin by equating each of the ratio to some constant called lambda. Now when you see that A by B equals lambda, so you can comfortably say that A equals B lambda and C equals D lambda and E equals F lambda. Now you can substitute the value of a, c and e in the numerator. So what you will get as a fraction, you will get p, and a can be written as b lambda to the power n plus q, and c can be written as d lambda to the power n, and r into e can be written as f lambda to the power n, and so on. Let's see what you have in the denominator. You have p b to the power n plus q d to the power n, r f to the power n, and so on, right? And this whole fraction has power 1 by n. Let's say each of the term of numerator has lambda to the power n as common. So I'll take lambda to the power n common, and in the numerator you will be left with pb to the power n, qd to the power n, rf to the power n, and so on, upon pb to the power n, qd to the power n, rf to the power n, and so on. And this whole thing has been rose to the power 1 by n. Now you see, you have the denominator and numerator as factors. So this can be cancelled with each other, and you are left with lambda to the power n raised to the power 1 by n, which is nothing but lambda. So yes, we can say this whole expression would be equivalent to the each of the ratio. One thing as a corollary you can notice, let's say I replace p, q, r with 1 and n also equals to 1. So this thing will become a plus c plus e and so on upon b plus d plus f and so on, and this will be equal to lambda. So you can also say that if you have a continued equal ratios, then sum of the antecedents upon the sum of the consequents would also be equal to that ratio. A very important two results which you need to keep in mind, because these two results would be acting as tools in solving many of the problems related to ratio. Let's try to solve this problem. Whenever you encounter problem, you should always try to read the questions properly and then try to put all your information there so that you can find the right answer. Let's say you have this ratio a by b, c by d and e by f, all three are equal. Show that a cube b plus 2c square e minus 3a square ef upon b to the power 4 plus 2d square by f minus 3bf cube is equal to ACE upon BDF. When you look, the first term of the numerator and first term of the denominator, if I take separately, I'll see a cube b upon b to the power 4. And if I take this as 2c square e upon 2d square f, and third ratio I can see is minus 3a square f upon minus 3bf cube. Now let's say I am going to call each of the ratio as lambda. I can say that b will cancel, so it would become a cube by b cube, which is equal to lambda cube. If I look here, 2 will cancel out each other. C by d is equal to lambda, so c square by d square would be equal to lambda square, and e into f would be equal to lambda, which is again lambda cube. And if I look here, I'll cancel this, f will make it square, a by b is again, this would be equal to lambda into lambda square, which is equal to lambda cube. So each of the ratio are equal to lambda cube. Each of the ratio are equal to the lambda cube. So sum of the antecedents upon sum of the consequent will also be equal to lambda cube, because we have already saw that corollary in the last theorem. So I can say the left hand side of this equation is lambda cube. Now what about the right hand side? Let's see. In right hand side you have a by b into c by d into e by f, which is nothing but a compounded ratio of the three ratios given, which means they would be equal to lambda into lambda into lambda, which is equal to lambda cube. Hence we can say that yes, it is true. Let's look at the second problem. You have x by a equals y by b equals z by c. Prove that x square plus a square upon x plus a, y square plus b square upon y plus b, plus z square plus c square upon z plus c equals x plus y plus z square plus a plus b plus c z square upon x plus y plus z plus a plus b plus c. Now if you look, this problem looks little complex, but if you look, it is very symmetrical also. You have x by a, y by b, z by c. So I can say the whole thing is equal to lambda to begin with. And I can also say that lambda would also be equal to x plus y plus z upon a plus b plus c, because sum of antecedents upon sum of consequent is equal to the ratio, because all the three ratios are equal. And why did I write it? Because in the right hand side you see the same symmetry, that x plus y plus z whole square plus a plus b plus c whole square upon x plus y plus z plus a plus b plus c, right? Now coming to the left hand side, the first fraction. This is your first fraction and it is written x square plus a square. So I can write my x is nothing but a lambda, y is nothing but b lambda, and z is nothing but c lambda. So my first fraction would become a square lambda square plus a square upon a lambda plus a, which I can say a square is common upon a lambda square plus 1 upon lambda plus 1. So this is nothing but a into lambda square plus 1 upon lambda plus 1, right? Same way, if I look here, it would be b square lambda square plus b square upon b lambda plus b, which will be written as b into lambda square plus 1 upon lambda plus 1. And similarly, the third would be written as c square lambda square plus c square upon what you call c lambda plus c. So c would be common and you would say lambda square plus 1 upon lambda plus 1. So what you notice that all the three fractions have a constant coefficient, that is lambda square plus lambda plus 1, lambda square plus 1 upon lambda plus 1, lambda square plus 1 upon lambda plus 1, and all have a, b and c as their respective coefficients. Now what about the right hand side? Again x plus y plus z can be written as lambda into a plus b plus c. So I'll substitute this, so you will get again a plus b plus c square lambda square plus a plus b plus c square upon a plus b plus c lambda plus a plus b plus c. So what you can do, it will again be broken into a plus b plus c as common, and the constant would be lambda square upon lambda plus 1. So definitely you see that the three ratios are a into lambda square plus 1 upon lambda plus 1 plus b into lambda square plus 1 upon lambda plus 1 plus c into lambda square plus 1 upon lambda plus 1. This is your left hand side and this is your right hand side, and you can say that both are equal because lambda square plus 1 upon lambda plus 1 would be common and it would be written as a plus b plus c into lambda square plus 1 upon lambda plus 1. So now the question looked little complex, but the symmetry of the question was very amazing. It was very symmetrical. So we were able to solve it in a very confident way. Let's say you have a homogeneous equation in xyz, and this xyz is proportion to three quantities, let's say alpha, beta, gamma, which means x is to y is to z is equivalent to, let's say, alpha is to beta is to gamma. Then each of x, y and z, x, y and z can be written as lambda alpha, lambda beta and lambda gamma. And this thing can be substituted in the given equation, something like, let's say, L into x can be written as lambda alpha cube and y can be written as lambda beta plus m, x can be written as lambda alpha and y square can be written as lambda beta ka whole square and z can be written as lambda gamma and n into y can be written as lambda beta square and z square can be written as lambda gamma square. The whole equation can be broken into this, and lambda to the power 4 would be common, and you will be left with L into alpha cube beta plus m into alpha beta square gamma plus n into beta square gamma square equals to 0. So this approach will really help you in solving many of the problems which we'll be seeing in our problem exercise. Let's look at this second theorem of ratio. It's a very amazing theorem. Let's say you have n fractions, a1 upon b1, a2 upon b2, a3 upon b3 up to an upon bn. And consider that all fractions are positive and a1, b1, a2, b2 all are positive numbers. And they are not equal, they are unequal. Then you are going to create a new fraction a1 plus a2 plus a3 up to an divided by b1 plus b2 plus b3 up to bn. This new fraction will always lie between the least among the fractions given and the largest among the fractions given. We have to prove this theorem. We'll begin with assumption that a1 upon b1 is the least and an upon bn being the largest. We'll begin with this way, right? And we are going to call that a1 upon b1 is equal to lambda. So definitely I can say a1 equals b1 lambda. And then you can say a2 upon b2 would be greater than lambda. So you can definitely say that a2 would be greater than b2 lambda. Same way you can say a3 upon b3 would be greater than lambda. So you can say a3 would be greater than b3 lambda. And so on, you will say an upon bn is greater than lambda. So you can say an would be greater than bn lambda. Now looking at these n inequations, I'll add all the left hand side together. So you can say a1 plus a2 up to an will definitely be greater than b1 plus b2 up to bn lambda times. So you can say that a1 plus a2 up to an upon b1 plus b2 up to bn will always be greater than lambda. So definitely we have proved the first part, that the sum of numerator upon sum of denominator will be strictly greater than the least fraction, that is a1 upon b1, which is equal to lambda. Now to prove the second part of the theorem, what we are going to do, we are going to assume that an upon bn is equal to k. We are going to assume that an upon bn is equal to k. So what you can say that an is equal to bn into k. Same way I am going to say a1 upon b1 would be less than k. So you can say a1 would be less than b1k. Similarly, a2 would be less than b2k. Similarly, a3 would be less than b3k. And I am going to add these all inequalities. So I can say a1 plus a2 up to an would be less than b1 plus b2 up to bn k times. So what you can say that a1 plus a2 up to an upon b1 plus b2 up to bn will be less than k, which is my largest fraction, that is an upon bn. So yes, we have proved successfully that if you have n fractions of same sign, then you can say the sum of numerator upon sum of denominator, the magnitude of this fraction would always lie between the least and the largest fraction available in the group. Now let's look at this problem. You have x upon b plus c minus a equals y upon c plus a minus b equals z upon a plus b minus c. You have to prove that x plus y plus z upon a plus b plus c equals x into y plus z plus y into z plus x plus z into x plus y upon 2x plus by plus cz. Now this problem looks a little complicated, but if you look closely, you will notice that your left hand side is nothing but the sum of antecedents upon the sum of consequent, because if you add b plus c minus a with c plus a minus b with a plus b minus c, you will notice that this b will be cancelled by this b, this a will be cancelled by this a, and this c will be cancelled by this c, and you would be left with a plus b plus c. So definitely I can say that this is nothing but equivalent to x plus y plus z upon a plus b plus c, that is sum of antecedents upon sum of consequence. So हमने left hand side अपना handle कर लिया. The left hand side has been tackled, that this will be equal to this. Now what about the right hand side? Now you see, with x you have coefficient y plus z, with y you have coefficient z plus x, and with z you have coefficient x plus y. So to begin with, I'll write x upon b plus c minus a, and I'll multiply this with y plus z in the numerator and in the denominator, which will be equal to y upon c plus a minus b, and you have to multiply z plus x upon z plus x, which will also be equal to z into x plus y upon a plus b minus c into x plus y. So what I see, that all the three fractions which I have written are equal and equal to the original fractions, and if I add all the numerators, I'll get the numerator of the right hand side. So that gives me a clue that the sum of whatever the denominator is would be equal to this. If I am able to prove that this plus this equals this, then the problem is done. So let's see. B plus c minus a into y plus z plus c plus a minus b into z plus x plus a plus b minus c into x plus y. So just notice that you have by, then you have bz, then you have cy, then you have cz, and then you have minus ay minus az. This is the first expansion. Let's look at the second expansion. You have cz plus cx, you have az plus ax, and then you have minus bz minus bx, right? In the same way, the third one you have ax, ay, bx, by, and then you have minus cx minus cy. Now notice that how many of them are being cancelled. So you have minus ay, which is being cancelled by ay, out, out. Now you have minus az, which is being cancelled by az, out, out. Now you have minus bz, which is being cancelled by this. So this is out, this is out. You have minus bx, which is being cancelled by this bx. So out, out. And then you have minus cx, which is being cancelled by this cx, out. Then you have minus cy, and then you have plus cy. Now you will notice that how many ax you have? You have one ax and one ax. That makes it 2ax. That makes it 2ax. You have one by, and then you have one by. That makes it 2by. And then you have one cz and then one cz. You have 2cz, which is nothing but your denominator. So yes, I can say that the whole thing would be equal to x into y plus z plus y into z plus x plus z into x plus y upon twice of ax plus by plus cz. So this problem had some calculation, but had you been confident in applying those results which you have learned, you would be able to see that only what you did was you just did little calculation. Now let's look at this problem. You have x upon L into MB plus NC minus LA equals y upon M into NC plus LA minus MB equals z upon N into LA plus MB minus NC. And you have to prove that 1 upon x into by plus cz minus x equals m upon y into cz plus ax minus by equals n upon z into ax plus by minus cz. Now this problem looks a little complicated. And whenever you encounter some complicated problem, the mantra is to begin with first step. And the moment you start your first step, you will start seeing patterns, you will start seeing things. Now let's say, if I see this problem, this part and this part, this gives me a little motivation because I see LA and LA will cancel each other and MB and MB would be cancel each other. So I'll try to first write a nice numerator. I'll write x upon L, y upon M, M will be cancelled here, and z upon N. I'll just write the numerator like that. And I'll try to add these two equations first, these two fractions first. So numerators plus numerator upon denominator will make the fraction same. So I'll say x upon L plus y upon M upon. Now LA out, MB out, you're just left with 2NC, which is also equal to y by M plus z by N, MB out, NC out, you will be left with 2LA, and the third one would be z by N plus x by L, and LA out, NC out, you are left with 2MB. Now all the three ratios have 2 common, so I'll just remove 2. I'll try to write it mx plus ly upon c into lmn, and this can be written as ny plus mz upon a into lmn, which is also equal to lz plus nx upon 2l upon b into lmn. Now lmn can be cancelled out, and we can simply write the first ratio as mx plus Ly upon C, Ny plus Mz upon A, and Lz plus Nx upon B. Now, this is what we have got from this. Now, key idea is to prove the second part of thing. And in second part, what I notice is bycz minus ax, czax minus by, and third ratio made by ax by minus cz. So what I am going to do, I am going to make the denominator here as cz. For this, I am going to make the denominator as ax, and for this, I am going to make the denominator as by. So I am going to multiply c with z here, and I'll just write z here. I'll just multiply a with x here, and I'll just write x here. And I'll write y here, and I'll multiply with y here. Now what I got my first denominator as by plus cz minus ax. So मैं इसमें क्या करूंगा? I'll try to write this ratio equivalent to the ratio which has denominator as by plus cz minus ax. So what I'm going to do? I am going to do by plus cz minus ax, means denominator of this plus denominator of this minus denominator of this. The same way I'm going to do numerator of this plus numerator of this minus numerator of this. So I'm going to do y into Lz plus nx plus z into mx plus ly minus x into ny plus mz. Let's see what I got. I'll just open up my numerator. The numerator would be Lyz plus Nyx plus Mzx plus Lzy minus Nxy minus Mzx divided by by plus cz minus ax. Now what I am going to see, my numerator, I have nxy and nyx, so I can cancel these two. I have mzx and minus mzx, I can cancel these two. So I am getting left with 2Lyz upon by plus cz minus ax. With the same symmetry, if you try to do that, I am sure you must have guessed the second one, this one. If you try to do the cz plus ax minus by, you can easily guess that that would be equal to 2m into xz upon cz plus ax minus by. You're going to do the same story, and in the third you are going to get 2n xy upon ax plus by minus cz. So what I did, I just followed the clue that I have to get this denominator, and by doing that, by creating that denominator, I did the same operations to get my numerator. And first I calculated this numerator, and by symmetry I can say the other two would be these two. Now if you focus in this equation, we have got our answer. How? Let's see. Our 2 will be cancelled, and then you have xy, then you have yz, then you have xz. I am going to write here z here. I am going to put z in the down. I am going to write x here, and I am going to put x in the down. I am going to write y here, and I am going to put y down. Now if you see, you have xyz, you have yzx, and you have xzy. So these three can be cancelled, 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 and what you got is n by z into ax plus by minus z cz equals L upon x into by plus cz minus ax equals m by y into cz plus ax minus by, which is your desired equation. So this problem looked terrible, looked difficult, but the first idea was, whenever we encounter a difficult problem, we have to begin with the first step. We followed the pattern, we followed the symmetry, and we started moving ahead. Once we simplified the complete ratio into this, we knew that we have to bring these ratios in the form of by cz minus ax, cz plus ax minus by, and ax plus by minus cz. So we just followed that clue and we tried to create ax plus by minus cz, ax minus by plus cz, and minus ax plus by plus cz, and we followed the same pattern for the numerator, and we got these equations. And these equations can easily be interpreted into this, because here z was a bit missing, I put z here and z here. Here x was missing, I put x here, and here y was missing, I put y here, and then x, y, z and 2 got cancelled, and then you are left with L, M and N with a desired x, y, z, and your denominator had already been found. So this was a difficult problem, but you should know this is the art of problem solving which you need to learn.